Low levels of energy were generated by these naturally occurring nuclear reactors. 1,000 standard light bulbs could be operated by the average power output of the Gabon reactors, which was around 100 kilowatts. Scientists have found a natural reactor that will alter the course of history forever. Keep in mind the future space so you can subscribe. Then let's not waste any more time and get down to the video. 2 billion years ago in the area now known as Gabon in Western Africa, 17 natural nuclear fission reactors were in operation, long before humans developed the first commercial nuclear power plants in the 1950s. Those natural nuclear reactors could only generate a small amount of energy. About 1,000 standard light bulbs could be powered by the average output of the Gabon reactors, which was around 100 kilowatts. 10 million standard light bulbs could be powered by the electricity generated by a single commercial pressurized boiling water reactor nuclear power plant. Although they only produce a relatively small amount of power, the nuclear reactors in Gabon are remarkable because they started working on their own around 2 billion years ago and have been running reliably for up to 1 million years. Furthermore, the fact that many radioactive fission products have been safely contained at Gabon reactors for 2 billion years demonstrates the viability of long-term geologic storage of nuclear waste. In the 1950s, when commercial nuclear reactors were first being developed and becoming popular, scientists first hypothesized that natural nuclear reactors may have operated on ancient Earth. In particular, in a paper published in 1956, Paul Kuroda theorized the conditions under which nuclear fission could develop and be maintained on its own. These conditions are strikingly similar to those found in nuclear reactors built by humans. Power is produced in nuclear reactors when uranium atoms fission or split apart, releasing nuclear energy. During this fission process, fast neutrons are created. These neutrons have the potential to trigger fission in other atoms if their velocity is reduced by a moderating substance. Nuclear fission can generate power in a self-sustaining critical reaction for a very long time, until the fissionable atoms in the nuclear fuel are all used up. Energy from nuclear fission is typically used to boil water into steam, which then turns massive turbines to generate electricity. Commercial nuclear power plants typically use uranium as their primary fuel source. Besides uranium-238 and uranium-235, uranium also exists as uranium-234. Fission is the most likely nuclear reaction to occur when neutrons are directed at uranium-235 because of its unique nuclear properties. On Earth, however, uranium-235 accounts for only 0.72% of the element, with uranium-238 constituting a vast majority, 99.275%, and uranium-234 present in only minute quantities, 0.006%. Due to the remarkably consistent isotopic distribution of uranium in Earth's crust, all uranium ore mined today contains about 0.72% uranium-235. Before it can be used as fuel in nuclear power plants, uranium must be artificially enriched to contain about 3% uranium-235. Water serves as both a moderator and a coolant in nuclear power plants to keep the chain reaction under control. The purpose of control rods is to regulate or terminate a nuclear chain reaction. These regulating rods are made from materials that can absorb neutrons without fissioning. To slow down or stop a nuclear reaction, boron can also be added to the water surrounding the reactor. Kuroda argued that prehistoric uranium deposits might have provided the raw materials for the development of a natural nuclear reactor. Although there are currently many concentrated uranium deposits, the development of nuclear fission cannot occur naturally. The reason for this is that a self-sustaining fission reaction cannot be maintained at the current uranium-235 concentration. Nonetheless, the ratio of uranium-238 to uranium-235 has been fluctuating throughout Earth's existence. Greater than 30% of Earth's uranium was uranium-235 when it first formed. Because uranium isotopes are radioactive and decay to other elements over time, the ratio of uranium-235 to uranium-238 has been fluctuating. Uranium-235 has been steadily depleted over the past 4.54 billion years because it decays at a faster rate than uranium-238. A self-sustaining fission reaction could have developed in uranium ore billions of years ago when the abundance of uranium-235 was high enough. The amount of uranium-235 present in uranium ore 2 billion years ago was about 3.6%, which is roughly the amount used in pressurizing boiling water reactor nuclear power plants today. Assuming the uranium concentration was high enough, a moderator was present and no neutron-absorbing elements were in the vicinity. A uranium deposit from antiquity might have developed self-sustaining nuclear fission on its own. It wasn't until 1972, 16 years later, that a natural nuclear reactor was found in Gabon. Once a French colony, Gabon is now home to uranium mines for nuclear reactors. The French made a startling discovery during an everyday isotopic measurement in Gabonese uranium ore. The ore lacked the typical 0.72% uranium-235 content. Instead, there was an extremely low concentration of uranium-235 in the ore, 0.717% to be exact. The French nuclear authorities took this seemingly insignificant difference very seriously. You see, the percentage of uranium-235 in the Earth's crust rarely deviates from the average of 0.72%. There was a pressing need to explain the whereabouts of this missing uranium-235, as the element is a key component in nuclear weapons. Thankfully, nuclear officials and scientists eventually remembered the old publications of Kuroda and others, and they quickly realized that the anomalous uranium from Gabon provided evidence of something extraordinary, the first natural nuclear reactor ever discovered. 2 billion years ago, some of the uranium-235 in the uranium ore was consumed in a natural nuclear reactor, leaving the ore depleted in uranium-235. In the end, 16 nuclear reactors created by nature were found in Oklo's uranium mines. However, researchers have a scarcity of uranium samples from which to draw. Back in the late 90s, mining operations near Bangombe threatened to destroy the world's last natural nuclear reactor. Physicist François Gauthier-Lafay published a 1997 article in Nature calling for a halt to mining in the Bangombe uranium deposit. Since their discovery in 1972, scientists have pondered the mystery of how and why Gabon's natural nuclear reactors came into existence 2 billion years ago but nowhere else on Earth. While research into the Gabon reactors is ongoing, scientists have made significant strides over the past 40 years in deciphering the complex mechanisms by which these nuclear power plants operated and were preserved in the geological record. You may be wondering, how is it that uranium-235 was depleted to less than 4% of uranium only 2 billion years ago, when natural nuclear reactors developed in uranium deposits? If uranium-235 levels had been higher earlier in Earth's history, wouldn't fission reactors have been more likely to emerge at that time? Keep in mind that a high isotopic abundance of uranium-235 is just one of 4 conditions needed for a natural nuclear reactor to develop. The concentration of uranium is also a necessary but not sufficient condition. 2 billion years ago, Earth did not have any uranium concentrations of any note. In a word, oxygen. A small amount of uranium can be found in some, but not all, rocks on Earth. Hydrothermal circulation, which picks up uranium and concentrates it in a new hydrothermal deposit, is the typical mechanism responsible for uranium concentration. The solubility of uranium is essential for its concentration via hydrothermal circulation. With more oxygen in the air, uranium became more movable and could be concentrated by hydrothermal processes. About 2 billion years ago, rich uranium deposits formed in a marine sandstone layer in the Franceville Basin in Gabon. Many tiny pieces of uranium-bearing minerals were originally present in the sandstone at the layer's base. Around 2 billion years ago, oxidizing waters penetrated the sandstone, scattering these minerals. Oxidizing waters dissolve uranium-bearing minerals, concentrating the element in several deposits near the sandstone surface. An extremely high concentration of uranium was achieved. In the Gabon uranium deposits where natural nuclear reactors developed, the concentration of uranium ranged from about 25% to 60%, which is close enough for fission to have begun at 10%. Friends, which planet has a natural fusion reactor? You can tell us in the comments section down below. That's all I have for you guys today. We hope the video was entertaining. The patronage of our audience is essential to our success. To that end, we encourage you to subscribe to our channel and stay tuned for more incredible critiques.